Hey, good afternoon, everyone. Welcome to the SLDS webinar. Our webinar today is on large language model training and coding. We have two young experts, Dr. Jiancong Xiao and Xiang Li, who have done significant high-impact research in this field and are well recognized in the community. Both of our presenters are postdoc researchers at the University of Pennsylvania, working with Professors Qi Long and Weijie Su. Dr. Xiao received his Ph.D. from Chinese University of Hong Kong. His expertise lies in statistical and deep learning theory with a focus on developing responsible and trustworthy machine learning models. Dr. Xiao's recent research focuses on large language model alignment, large language model training and fine-tuning, adversary robustness, and classical learning theory. His research has been featured at top journals and machine learning conferences such as JASA, NeurIPS, COLT, ICML, and ICLR. Dr. Xiang received his PhD from School of Mathematical Science at Beijing University. His research lies at the intersection of statistics, stochastic optimization, and machine learning, with a recent focus on large language models. He made significant contributions to federated learning, stochastic approximation, online decision-making, and online statistical inference. Recently, Dr. Li investigates statistical watermarking to ensure the provenance and robustness of AI-generated content and develop tools to evaluate how LLM encode and use knowledge. His work has been featured at leading machine learning conferences, including ICML, ICLR, and NeurIPS, as well as in top journals such as Journal of Machine Learning Research and Annals of Statistics. Without further ado, let's get started. So, Dr. Xiao, the floor is yours.
Okay, thank you very much for the introduction and for the invitation. Today, our topic is large language model training and coding for statistical learning and data science. This is era of LLMs, and nowadays everybody use LLM. And as statistical researchers, we aim to explore the statistical issues and statistical topics on LLM. And there are many topics about alignment, evaluation, watermark, and today's talk in the first half, I will focus on the alignment. Why large language model becomes very powerful nowadays? One of the key algorithm behind is the aligning large language models with human feedbacks. And the most important algorithm is called reinforcement learning from human feedback. It usually contains 3 steps. The first step is SFT, which stands for supervised fine-tuning. And the second step is to train a reward model. And the last step is to maximize the reward using reinforcement learning. Usually before the first step, SFT, we usually have a step 0 called pre-training. And here in the mathematical notation, the pi file is the large language model, which is parameterized by the phi. And we aim to maximize those parameter phi to obtain a very good large language model. And here x1, x2 to xt are different tokens of a sentence. So large language model is a next token prediction model. Given the tokens x1 to xt minus 1, we want to predict the next token xt. And finally, the loss function is to maximize or equivalent to minimize the negative log likelihood function. So this is a very basic and classical in statistics, and it usually the large language model is very large, and also the data set or the corpora is very large. So it usually takes several months or hundreds of GPUs to obtain a pre-trained model. So our focus is not on the pre-training step. We start from the step 1, which is called SFT. First of all, we would obtain a small data set of SFT. It requires the prompt and answer pairs. The loss function is very similar to the loss function of pre-training. The only difference is that here we given the prompt X and we aim to predict the answer Y. And finally, we can fine-tune model on this SFT dataset, and the obtained model is usually called the SFT model. Given the SFT model, the step 2 is called reward modeling. We use a reference model, which is usually the SFT model, and we have several prompts. We let the reference model to give us two different answers, Y1 and Y2, that correspond to this prompt. For example, the question is, how often are the Olympics? And the first response is that it is estimated every 4 years. And the second one is, for 2017, it was every 4 years. So obviously, the first one is better than the second one. Then human labeler could express their preference, or YW and YL, and therefore we label the first one as YW and label the second one as YL. And repeat this procedure, we can collect a preference data set. For this data set, we call it a D comparison. So it is a D with a subscript comp. And we can have a reward model. We call it R theta XY. It is parameterized by theta. It is also usually a transformer-based large language model. The input is both the prompt, all the answers, and the response, all the uh, I'm sorry, X is the question and Y is the answer. And the loss function of reward modeling is to minimize this cost entropy loss on this comparison data set. And finally, we can obtain our reward model. The last step is to fine-tune the large language model using reinforcement learning. We can look at the first term. The first term is the reward. So given a prompt X, we can sample answer Y here, and for the sample Y, we aim to maximize its reward. And for the second term, it is a regularization terms, which corresponds to a KL divergence between the trained model and the reference model. The goal is that the trained large language model cannot be moved too far away from the reference model. Otherwise, the training will fail. So this is the background of reinforcement learning from human feedback. And uh, this pipeline is usually very complicated. We need to obtain a reward model first and then obtain a large language model first. So a very famous technique is called direct preference optimization, which combines step 2 and step 3. And then we don't need to train a reward model. We can directly obtain our large language model. The idea is very simple. First of all, in mathematics, we can write down the closed form solution of this optimization problem, and then we put that closed form solution into the loss function and of the reward model. And finally, based on some calculus, we can obtain such a loss function called DPO loss. Okay, this is the background of RLHF. And today our topic is LLM training and coding, right? So previously we only introduced the mathematics. So how to implement it in how to train our own models. Because many of the statisticians are not so familiar with LLM coding. I want to talk about it. Here I want to introduce two very useful open source RLHF framework. The first one is called OpenRLHF, and the second one is called Transformer Reinforcement Learning. Both of these two packages are publicly available at GitHub. Using these two framework, we can easily train our own large language model. First of all, how to install this package? We use the OpenRLHF as an example. First of all, you need to be able to connect to a GPU server, because you cannot train a large language model on your own laptop, right? Although otherwise, if you are not able to connect to the server, you need a cluster that you can submit your personal task to that cluster to train a large language model. Both ways is fine, but And then once you connect to your GPU server, you can activate or create your own training environment. Otherwise, for example, your Python version may conflict with your colleagues. So you need to have your own environment. And based on the official description of OpenRHF, it is recommended to launch the Docker kernel based on this command. And then you have your own environment. And the next step is to install the OpenRHF. This is very simple. The command is to pip install our OpenRHF. And then you're all set for OpenRHF. And then the first step, how to train your own SFT model. The package contained many training scripts, and here is the address of the file. You to to run this training scripts, you only need to bash your training file, and this is the way you can connect to your server. If you need to submit a task to the cluster, the command is different and depends on how your cluster work. And then within this training script, you can set many hyperparameters for training. For example, the first one is the maximum length of the responses. In this way, you can set it to be 2048. And similar, you can set your own training batch size. And for example, you can set the learning rate. Most importantly, you should select your own data set and you should select the pre-trained model. And in this training script, the default setting is the Llama 3AB model. You can replace it by the Q1 model and many others. And the default data set is this one. If you want to change your own model in your personal data set, you can replace it. But the structure of your data set should be the same as the data processes that use in this. I see there is question or is there any guidance available on choosing the training hyperparameters? In my opinion, it's very hard to answer this question because for different scales model, the hyperparameter is different. I think if you change a model size like a 7-bit or 8-bit, you just need to use the default setting. If you don't have enough GPU, then you could choose the training batch size more smaller. For example, 128, for example, and 64. But usually you don't need to change the learning rate. This is my answer. But if you want to train a very large model, for example, the 70 billions model, and to be honest, I don't have this experience. I don't know how to set the hyperparameters for those large models. And once you obtain your SFT model, you can try to train your own DPO model. And the procedure is also very simple. There is a training script in this address. The file is called train DPO llama sh. And again, you can set the hyperparameters inside this file. And in this way, the pre-trained model is usually your trained SFT model. Here, the default one is the Llama 3 AB SFT mixture, but you can replace it by your own trained model that we trained in the previous steps. And also, the data set for DPO and for alignment and is different from the one that used in SFT because here the dataset is usually a preference comparison dataset. And this is also one of the publicly available dataset in OpenRHF. Okay, in this way, you can very easily train your own large language model. The only difficult thing is that you need to have enough uh, enough GPU. Okay, so having introduced uh, the basic concept of the training large language model, we want to talk about some statistical topics and issues for fine-tuning or post-training. The first one I want to introduce is called calibration. The definition of calibration is that the prediction of the model should equals to its accuracy. The accuracy is usually defined as the observed frequency of the correctness. In the GPT-4 technical report, it is report a very severe issues that the aligned large language model is usually poor calibrated. It is reported that the pre-trained model is well calibrated. A model of well calibrated usually looks like a stairway in this figure. But after the preference fine-tuning, here the uh, model equals to PPO. PPO is one of the algorithm for reinforcement learning from human feedback. It is found that after RLHF, the model becomes very poor calibrated. Uh, the model usually exhibit overconfidence. For example, for a question, if its confidence is about 60% like this, and finally its actual accuracy is usually very low. In this way, it is lower than 40%. So and based on further experiment, we find that this is a very universal issue. It across different approach, no matter we use what kind of algorithm, reinforcement learning or from human feedback and DPO, and no matter what models we use, other than ChatGPT, when we use Llama or Mistral, all kind of this model, we'll see that this is a very important issues. And also the first figure is about the pre-trained model, and the last figure is about the model of reinforcement learning from human feedback. So what about the SFT model? In our experiments, we found that the SFT stage is also very important. So we can first take a look at the default settings in SFT. It is about the class which is called a SFT configuration. And in the default setting, the fine-tunings are fine-tuned on both the prompts and the answers of the training data set. Here is an example. First of all, from the TRL package, which is the transformer reinforcement learning I introduced before, we import a class called a SFT configuration. And in the second line, we can initialize this class, which is called SFT configuration. And then we can initialize our SFT trainer, and the last line is about the SFT configuration. So using this default setting, the fine-tuning is applied to both the prompts and answer. And based on our experiments, we find that if we only fine-tune on the answers, but not on the prompts, the calibration can become much better. So I think this is a very useful trick that I want to introduce. But how to fine-tune only on the answers? This is another class called a data collector for completion only LLM. It is also a class from the TRL package. And after initialize the SFT configuration, we can initialize a collector, which is correspond to this class. Data collector for completion. This is very important. And when we initialize the SFT trainer, we need to add another lines about the data collector. If without this line, it will use the default collector that fine-tune on both the prompts and answers. And based on using this very simple checks, we can find that the model can have a much better calibration. And first of all, these tricks can be applied to the SFT stage, which is the step between the pre-trained and the DPO. And also we can apply it after the reinforcement learning or DPO. And we'll see that the uh, expected calibration error will become much smaller. But only using these checks, the calibration will become much better. But we cannot achieve a perfect calibration in this way. If we want to achieve a perfect calibration, look like a perfect stairways, we need more work to do. But the algorithm is much complicated and it is not covered in our talk. If For those who are interested in this topic, we refer to our paper. And for this talk, I only want to introduce some useful checks that can improve the calibration, which is the disk collator and fine-tune only on the answers. This is uh, the first statistical issue I want to introduce. And the second one is called the preference caps. This issue is very similar to the last one, but it's a little bit different. For example, if we want to fine-tune a large language model on human preference, given a prompt, we have two response, and about 60% of the people prefer the first one, and 40% of the people prefer the second one. And after the reinforcement learning from human feedback, in the LLM preference, the LLM will strongly favor the first one and totally ignore the second one. So this phenomenon, I call it a preference caps. Uh, for some math reasoning problem, this is a desirable phenomenon, but in a broader context, for example, the habits between different peoples, the foods different people likes, it is undesirable to ignore all the minority preference. So this is a statistical issue we call the bias in alignment. And this is not only about fairness, but also about the decision making. For example, if I ask a question, should I start a pizza or sushi restaurant? So in different places, the answer is different. In Italy, people will prefer the pizza, but in Japan, people will prefer sushi. So the question is how to align large language model to completely preserve the human preference. So the question is very simple. If human preference is 6 to 4, how can we make the LLM preference is also 6 to 4? We consider the mathematical parts first. We still aims to maximize the reward plus a regularization term. And previously, the regularization term is the KL divergence term. But here, we can apply all kinds of the regularization. The goal is that the optimal solution of this problem is correspond to the BTL model. The BTL model is the assumption behind the human preference. And finally, we can prove that uh, the global solution of this problem is a preference matching policy if and only if the regularization term takes this form. The first one can be viewed as an entropy term, and the second term is a constant, and the last term is a constant over the policy. If we simply set C1 and C2 to be 0, it is entropy terms, right? So we prove that to address the preference collapse issue, adding an additional entropy terms is very important. So in the original objective function of reinforcement learning human feedback, we add an additional entropy terms in medium. And I see there is a question. How we can get recording of this meeting. And yeah, I think Suha can address this issue. And And then we want to get a corresponding DPO version loss of this one. And by some mathematical calculation, we can have a closer objective function like this, that the optimal solution is correspond to the RHF objectives with an additional entropies. Uh, there, there are some difference. First of all, in DPO, the first coefficient is only beta, not with the alpha. And in the power, it is 1, and also not with the alpha. So if we simply set alpha equals to 0, then this loss function is reduces to the loss function of DPO. And okay, and then how can we implement it in our coding? First of all, we need to delve into the DPO loss, right? The coding is very simple. First of all, for the log ratio of the large language model pi, we need to change the coefficient from self dot beta to alpha plus beta, and the coefficient of the second one of the reference model is still the beta. Then we are done. So this is a very simple tricks to modify the original DPO loss. So I think everyone can do that. Did very simple tricks, and I find this is a very useful tricks, and we can take a look at some experiments. If we use this preference matching of DPO, we can see that the mean of the KL divergence will be much smaller than the previous one, which means that in this way we could get a smaller divergence between human preference and LLM preference. So this is how to resolve the second issue that I introduced. And uh, this is the end of the first half, and thank you very much. If you have any questions, I will leave it to the Q&A part. And so let's welcome our next speaker, Dr. Xiang Li.
Hello, everyone. Just now, Jiancong introduced the post-training technique for large language model and his research along preference alignment. Now, let's move to the second part. I will introduce how to use APIs for model evaluation and how to embed and detect text watermarkings. So at this point, I think I don't have to spend more time to explain why large language model is so powerful. It's already used in other aspects of our daily life, like chat, generation text, translation, answer questions, and code generation. While in these applications, for most cases, what we only care is the output of the models. So in conventional interaction with the model, we do this by the web interface. But this is not that convenient. So in practice, developers and the users generally use these models by API, that is application programming interface. So from a high level, API allow the developers and the users to query the model in a black box manner. So you put your questions and your requirement, and then you get the answers, just like you call a Python function and you get the result. So this convenience enables a lot of applications. For example, chatbots, assistants, writing tools, coding generation, summarizing materials, and the knowledge extraction, and doing some deep research. But keep in mind, in these applications, API only serves as a reasoning engine. It generates the intelligence responses. But for the exact API, typically practitioners will wrap it with some other modulars like user authentication and text billing, something like this. So now let's get started with how to use these APIs. I will focus on ChatGPT from OpenAI, but this process is quite similar for other companies, such as Gemini from Google. So first of all, you should have an OpenAI account. You could register account by this link, or you can find all of this from their official website. But here I list some key steps, and then get the API keys. The API keys is essentially an identifier of yourself, because API is not free. But now this is quite cheap now. For example, for GPT-4 Mini, the cost is about $0.15 per million input token, and then only about $0.60 per million output tokens. This is actually much cheaper than 3 years ago. And once you OpenAI will send the bills according to the API key. So if once you get the API key, please keep it secretly. Otherwise, other people use your secret key could query the model, but the cost of the bill will send to you. So in general, this key will be a very long string. For OpenAI, it will start with SK hyphen and some random numbers and digits. Once you obtain the key, then we could query the model now. Here, I provide a minimal Python example. In the first line, we import the package OpenAI. And in the second line, we initialize a client object. Here, you should input your secret key, because this will allow the OpenAI to track the billing information. And then what's the most important step is this part. That is, we should identify two arguments. The first one is the model. From which kind of model you want your response from. Here, I choose GPT-4 Mini. And then the message, or in other words, the questions. It consists of two parts. The first part is the system prompt. It's generally a high-level instruction or guidance about how you wish the model to generate. Here, I type, you are a helpful assistant. But in general, you could input more, such as, please make your answers brief and easy to understand. Please use comma to separate different points. Please be polite and not be malicious, something this high-level guidance. And then you input your question into the user prompt. This is basically the question that you want the model to answer. Here, I choose explain PCA in 3 short bullets. So after this line is called, all of generation results will be collected in this RLSP object. It's in fact a multi-layer structure containing a lot of information about this generation and answers. But if we only care about the final responses, we could simply call this line, that is resp.choices.message.com, and then I provide example of the model's output. It provides 3 bullet points to explain what is PCA. While except the model and the message, ChatGPT API also provide you more choices to control the generation behavior. The most important is the temperature, which is a scalar that controls the randomness of the model responses. In general, if you set the temperature to be very small, like 0, then the responses will be generated quite deterministic. But if you set it quite large, like say 1, 1.1, or 1.3, then the responses will be quite random. But do not set it too large. For example, 2. If you set it too large, then the generation will be quite purely random, and it will generate some random words, random nonsense sentence. Another is the argument is the max tokens. It limits the output length. And the top P parameter, which is a probability that are used in the nucleus sampling. This sampling is basically to truncate the tail the tail of the token distribution, such that it will be more concentrated on the topest tokens. And some penalty parameters that either discourage or encourage new tokens. The usage is quite similar. you simply specify them and use it as before. Beyond the chat, OpenAI API also provide other functionalities. For example, it allows you to embed your text into a vector such that the distance between vectors correspond to the semantical similarities between your different input sentence. And it also allows you to generate images or call some external tools such as Google engine or manipulates or organize your data into a certain format. Interesting is that you could also use OpenAI API for fine-tuning. Just as Jiancong mentioned, Jiancong introduced his proposed new method. But if you do not care too much about the novelty of the method and try to some classic or default choices, you can also use OpenAI API to that aim. All you need to do is that you collect your domain-specific data, preference data, in a prescribed format, and then input your data to the API, and then it will return a model ID, and the OpenAI will train a fine-tuned model using your input data on their server side, and give you an ID to index the fine-tuned model. And then you could call the fine-tuned model as before for your following downstream tasks. So now I have introduced how to use the ChatGPT APIs. An important point I want to make is that even we only know how to use the APIs, we get the response from the large language models, we could still do meaningful statistical research. The reason behind this statement is that API only provide an access to the large language model reasoning or intelligence, but how we interpret their results, how we improve the usage of these responses requires statistical thinking. For example, suppose we want to know how many theorems a large language model knows. The easiest way to measure is that we simply ask the model, please list all the theorems you know. Definitely this measure is naive and is not satisfactory because the model generation is random. There must be some knowledge or some theorem names the model knows, but it will never express in his answers. So a better way is that I ask multiple times and collect the unique theorem names from this bunch of interactions, just like this second figure shows. So I ask the ChatGPT 100 times, and each time I ask the model to give me 20 theorems. So after this query, I will collect 2,000 theorems. But this method is also limited because given this limited number of queries, it means that the large language model knows theorems no more than 2,000. So this is also unsatisfactory. So in our recent work, we propose a new method that's to estimate the unseen knowledge. The unseen knowledge basically means that the model actually knows, but it's fair to express or reveal in a limited number of queries. So our method is basically a 5-step procedure. We will, for a fixed prompt, we will ask the model to generate responses. And we will collect a bunch of responses. And the second step, we will verify it using some external database. This step aims to remove some hallucination. Okay, try and ensure that all the answers are correct. And in the third step, we will cluster these valid names according to their semantic meanings. This is because language are redundant. For a given theorem, it might have different expression. It has different names. For example, the Bayesian theorems, the theorems of Bayes. So it has 2 names at least. And now, once we have these unique clusters, we estimate the prevalence, which is the number of unique clusters that appear exactly S times. So we will have S1, S2, S3, S4. And from this, we have N1, N2, and 3. And from these ni's, we will recover, we will estimate n0. Here, n0 is exactly the number of theorems that appear 0 times in our queries. And then we sum, in order to obtain the final amounts of the model knowledge, we must edit this n0. So now let me show you our results. We create 9 models, n query times with a fixed prompt, like please give me NANS mathematics theories. I want to check your knowledge about mathematics theories. And we will use Wikipedia to verify whether the theory is valid or not. And we will cluster the theory names based on their unique external identifiers. We also define an additional measure, SKR, that is the same knowledge ratio. That is the ratio of the observed knowledge divided by total knowledge. Here, the total knowledge is the sum of seen knowledge and unseen knowledge. So now here is the table summarizes all of these results. So we can see that first, for all models, the SKR ratio, the SKR is strictly less than 1. It means that all the model will hide some information and knowledge when we try to evaluate them. Second, when we take those unseen knowledge into consideration, this will change the order, the comparison order of different models. For example, if we look at the first 2 models, ChatGPT 4.0 and ChatGPT 3.5, if we only focus on the NC, the observed knowledge, then we conclude that the ChatGPT 3.5 is better because it's no more. But if we incorporate those unseen knowledge, then we will conclude that this ChatGPT 4.0 is better because its total knowledge is much larger. So in this way, our procedure of estimating the unseen knowledge provides a more complete perspective to evaluate the model capability. So now, just now, we only could observe the outcome of models. So what if we have more access to the large language models? To answer this question, we first should know how a large language model combines different tokens. Here, I will use WT to denote a token, and a text is a sequence of tokens that I denoted by W less than T. So large language model generates tokens autoregressively. It means that at each time, it will input a preceding text into the model. And then the model will output a token distribution, PT, and then sample the next token, WT, from it. And they will extend the history by appending this new token to the history. The model will generate this process until a maximum length is achieved or some stopping criteria is met. So here is an example. Suppose I saw cat owner, this 6 token prefix to the model. The model then give a token distribution. Assume that the top 4 tokens are this, and by sampling, we sample the next token copies. So if we could control the sampling process of a large language model, then we could manipulate the randomness. Here, I mean that we could embed a secret statistical signal between the input, that is the preceding text, and the output, that's the next token. And then we'll create a secret statistical signal. And this signal rarely appear in human written text because humans do not know this kind of signal is they do not know how they are generated. But this signal will deliberately appear in model generate text because this is what we do to generate these tokens. Well, this technique is known as text word marking. It enables us to detect whether a given text is generated by large language model or written by human probably. And this philosophy behind this technique does control the sampling of the generative AI models could be applied to other data modalities such as images, tabular, audio, and video. And it has a lot of applications. So now let me introduce a little bit more detail. We still generate the NTP distribution as before, while the only difference is that we will use the preceding text to generate a random seed. And we will sample the next token using this particular random seed. In order to compute the random seed, we will use some hash function or random seed generator, which I denoted by this A. So mathematically speaking, the watermarking generation simply is to first compute or generate a random seed by using the prefix text and the secret key together with the hash function A. And then sample the next token according to this NTP distribution in this particular random seed. So mathematically speaking, a watermark is defined by this tuple AS and a secret key. This key will be revealed only to the detector, so common users will not know this. And the watermark signal is the dependence of each token T on these pseudo-random numbers. And then now you can see why I say that watermarking signal is a dependence of the token on its preceding text, because this pseudo-random numbers or random seed is computed using this prefixing text. So here I provide a further example. So the only difference is that we use the nearest 4 tokens to compute the random seed using the hash function A and the key. And this random seed will be used to sample the next token. The everything else is still the same as before. The only difference happens in the sampling process. So now let me give more comments about these pseudo-random numbers, because for statistician audience, the pseudo-random numbers and hash functions is hard to understand. In general, this hash function will take input, take 2 kinds of input. The first one is the public data. Here we choose the previous token history or simply a short segment. And then private information. Here is the secret key. So it has a nice property that as long as the inputs of the hash function are different, then the output of the hash function could be viewed as ID. And once we vary the key, the secret key, the output of the hash function is statistically independent with this public data part. And in general, it's hard to guess the secret key from the outcome hash function and the preceding text. Well, so the next question is how to find this hash function. Well, in general, this topic is well developed in the field of computer science, in the cryptography literature. So here I will not mention too much about it. But in theory, when we develop mathematical theory to explain the goodness of the watermarking and its detection methods, we assume this delta T hash function are truly ID. But in practice, the implementation uses deterministic generation, such that we could recover those pseudo-random numbers when it comes to detection. Okay, here is the pseudocode for watermark detection. As I mentioned, it generates PT, then computes pseudo-random numbers and uses to sample next token and append history and repeats until we generate a full response. So now once I introduce how we embed watermark, then it comes to how to detect it. So in the we could resort this to a hypothesis testing framework. Under the non-hypothesis, the given text is assumed to be human written, right? Under under the alternative hypothesis, the given text is generated by a large language model. So the intuition is that under the null hypothesis, the tokens will be independent with those pseudo-random numbers. The reason is that the human users do not know any information about the hash function and the keys. So when they generate tokens, they generate them according to their will. So we could confidently view them as independent. However, for large language model generated text, these tokens will deliberately depend on these pseudo-random numbers by the decoder function S. So in other words, watermarking couples each token with a recoverable pseudo-random number zeta t and changes their joint distribution from independence to a specific dependence. However, independence test is not very satisfactory in practice because under the null hypothesis, there are a lot of possible candidates distribution. So in practice, the literatures and the existing works often resort to a pivotal statistics. Here, the pivotal statistic is the scalar function that takes the token and the pseudo-random number as input and output a scalar. It has a very nice property that is once WT is independent with the pseudo-random numbers, the output will always follow a null distribution. Here, I denoted it by mu0. While under the alternative, the WT will depend on these pseudo-random numbers by this decoder S. So the pivotal statistic will follow another distribution. Here, I denoted it by mu1 PT. So then, detect watermarking is basically reduced to detect the distributional distributional differences in the sequence of Ys. So in practice, the detection procedure go in the following lines. From a given sequence of tokens, we first use the knowledge of the hash function and the secret key to recover all of these pseudo-random numbers, zeta, and combine both tokens and zeta to compute this pivotal statistics. And then we apply a score function. And if this score is larger than a threshold, then we claim the given text, the given sequence of tokens is watermarked that is generated by a large language model. Otherwise, we claim that there is no sufficient evidence to support this. So here is the pseudo code, but this is basically the same thing that I introduced before. It's worth to mention that because under the null hypothesis, YT will always follow a node distribution. This probably allows us to control the type 1 error rigorously. So now let's move. Once we compute these Ys, the sequence of pivotal statistics, the remaining question is, how could we choose the score function? So now this question is basically a statistical question. And we could find a lot of tools or ideas from conventional statistical literature. So in our recent work, for these sum-based rules, that is universally apply a score function H, we introduced an efficiency measure. This measure is basically quantifies the exponential decay of the type 2 error when we fix the type 1 error to a given level and sets the text length to infinity. So by maximizing this efficiency notion, we could find a closed form expression of this optimal score function. And we also propose some truncated goodness fit test for corruption case. The reason is that in this formulation, we assume that the given text is either fully human written or fully large language model generated. But in practice, we will often confront cases like the text is generated by large language model first, and then human will modify them a little bit. Imagine that how you polish your paper and some other document. So in this case, the text should be modeled as the mixture of model-generated parts and the human-written part. So we developed a truncated goodness of fit test for this mixture case, and prove this test is optimal in certain regions. And very recently, He et al. They show that in general, for general goodness of fit test, like a Kolmogorov test and some chi-square test, they could generally improve existing watermark detection in both detection power and robustness to these human corrections. And very recently, Tsai et al. They derived optimal score functions when we cannot treat pseudo-random numbers as IOD. So now, in fact, this goodness fit of test perform well, and in the no corruption case, while under some human edit, it's still quite robust. Okay, so now I have introduced how to embed watermark and detect watermark, but I basically introduced them using the pseudocode. But there are still many other things if you want to implement them, such as how to load the model, how to load the data, how to set the GPU, or how to implement different detection rules. And I provide a self-contained watermark Python demo in this link. It contains only about 200 lines. So you could change some parameters, change the model, or test your own detection rules, or your new developments of watermarking schemes. So now let me conclude my talk. So in the first part, I introduced how to use ChatGPT APIs. A main point is that even use APIs, we know how the model answers some questions, we could still do some meaningful statistical research. And then if we have more access to the model, like say we control the sampling process of the model, then we could embed watermark signals. It's basically couples each token with some recoverable pseudo-random numbers. And there are a lot of follow-up statistical questions about watermarking, such as the detection, how many contents are watermarked, and which contents are watermarked. Finally, if you are interested, please have a try to watermark. That's all my presentation.
Thank you so much. And let's move to the Q&A session.